All right, so you should be able to see me here and hear me as well. I see a few noting faces. So hello, everyone. As said, my name is Romain. It's my great pleasure to kick off this workshop. Well, kick off. Today, I'm going to talk about this work I've been doing. It's called TriScale. And more specifically, what we're going to talk about is those two key questions that are how to design experiment and how to analyze the data that one collects. There's going to be a slight focus on networking, but it's actually quite general, as you'll see. And more importantly, we're going to talk about experiments that aim to assess the performance of an algorithm, a system, whatever you might be working on. And as I said already, the goal is to really foster the replicability. And what I mean by replicability, we're going to talk about a bit later in the introduction of the tutorial. But before this, a few notes about how this tutorial is supposed to be run. So if you manage to stay connected to the internet, then I would really much welcome questions during the presentation. And for that, I would prefer the questions on Slack so that I may eventually have time to get back to it after the presentation. But otherwise, if that should not be possible for any reason, the Zoom chat is of course also okay. If you have questions like clarification of things I say, you can also write them, and they will be relayed to me by Marco directly by voice. There will also be 2 dedicated time slots during the presentation for Q&A that I'll show you in a second. So during those Q&A slots, don't be shy. You're more than welcome to just unmute yourself and ask the question directly, but other than that, please stay muted for the rest of the presentation to avoid disturbances. So the plan for today, I will start with some introduction about what I mean by replicability and why it matters to us, and we'll take a few examples to discuss that. Then we will enter the main part of this tutorial. It's going to be about see concretely what you can do in order to foster the replicability of your experiments. And I'll try to convince you that it's actually not so hard. And there are a few things that you can do, practically very concrete things you can do to improve things from the state they are in now. So they will comprise of 3 parts. First, I'm going to try to understand what variability actually looks like. Then there's going to be a short part about some basic statistics knowledge that are actually required in order to discuss those things. But fear not, I promise this will be light, and you will see that actually the pieces of statistics I'm going to talk about are very basic and surprisingly enough, not really taught. At least I discovered them during my PhD while I was working on this project. And I think it would benefit for having this as part of the curriculum of any scientist nowadays. But anyway, the third part finally will be to see how we can combine the knowledge of how the variability looks like and some basics about statistics to actually derive a concrete methodology to foster replicability. And then finally, the last big part of this workshop for which we should have at least 30 minutes would be an actual hands-on session where I will show you how you can apply this tool, this TriScale framework. You don't need to install anything, just open a window in your web browser and then you can access the tool and play with it. I've prepared some materials for you to discover a bit the API of the framework and what you can do with it already now, based on what I covered in the tutorial. So there will be, as I said, 2 Q&A slots, one after the stat part, which usually triggers some questions, and one after we're done, just before we move on to the hands-on part. So on those 2 time slots, I'll take more general questions about the presentation. Okay, so let's start with discussing what is replicability, right? What does it matter? And for that, I would like us to place a little situation. So let's say we have a new research team that designed an algorithm, we'll call it Banana, and it's ultra low power, it works super well, and it outperforms all the competition, right? And so obviously they need to set up an experiment to validate such a claim, right? They cannot just write that in their paper and be done. And so here is what they do. Right? They deploy banana on some real test bed. Many exist, and you can pick the one you like best. They pick one specific benchmark problem to assess the performance of their protocol, the banana protocol, and then they compare that to the state of the art that we'll call Kiwi. And so they run both head-to-head in their experiment so that they can really compare. And they do this comparison, they run this benchmark problem, let's say 10 times. Okay. Now here is, on top of my head here, the summary, the plot they prepared to put in their paper. So we have normalized energy consumption, so normalized with respect to banana. So the median of banana is 1, and if the median is 1, then the corresponding median of kiwi is a bit below 2. Now in their paper, they write that banana achieves a 2x improvement over kiwi. We're quite familiar to see such claims in papers. I'm sure you've read such sentence many times. But now let's say that you are reviewing that paper. But you're reviewing this paper, and then I'm asking you, do you think that 10 runs are really enough to support such a claim? And if not, how many runs would you ask as a reviewer to believe the claim of a 2x improvement? I'll let you think about that for 5 to 10 seconds. It's not so easy, is it? Actually, you cannot really answer those two questions. And why? Because it's kind of underspecified. We don't really know what type of performance we're talking about. What does that mean? A 2x improvement? Improvement over what? Right? Like, there are tons of things we might want to consider in terms of performance. So it's not really clear, and yet we see such things quite often. Now let's say, for the sake of argument, that the authors clarify their claim and then say that they improve 2x in the medium case. So it's more specific, we know what we're talking about a bit more. Now, second question, if you would do again this experiment, you rerun banana and kiwi, how likely do you think it is that you would obtain the same results? Again, 5 seconds, think about that for yourself. It is kind of hard to say. It's kind of hard to say. Like we have the median, we have some kind of spread for the results, but what does that mean, obtaining the same results? Like, we don't really know still how we would formalize this. And the reason we don't know is that because those are hard questions. Like, they're super basic, but any way you look at it, it's not so simple to find answers or to derive a way to answer those questions. And that's exactly what this tutorial is all about. Like, in this tutorial, this is what I'm going to discuss. I'm going to present you some sound methodology to provide rational answers to those questions so that you can define how many runs might be at least required, how many runs are required for making a performance claim, and to be able to draw some results about replicability with a certain level of confidence. And so this methodology I'm introducing now as what we call TriScale. So I promise a clarification about what replicability is. So on this graph on the left, you don't have to look at all the details right now, there are quite many. What is important to observe is that there's a classification between the two columns, between whether two classes of scientists are using the same data, that's the left column, or using different data, that's the right column. Sorry, it's too far off, I cannot point it better. So this is one dimension of classification. The other one is whether the two scientists, the two teams, use the same analysis, so meaning the same scripts to process the data, or they use different analysis. And so this classification allows to differentiate 4 different notions, and replicability is one of them. Replicability is generally understood, and would be the case for today, as running the same analysis, so same processing, same definition of metrics, and so on, but with different data. So we had our example before, kiwi versus banana. The authors do it once, they run, let's say on FlockLab, they get a set of experiment. Replicability is you or me, we redo the entire experimental campaign, and then we compare, do we obtain the same results or not? This is replicability as we're going to talk about it today. Now, does it matter? Oh, why does it matter? Well, if you think about it, if you cannot replicate, that's not really science. Like if you make a claim that no one can reproduce and verify, then this means that it's either just pure luck or it's just a random phenomenon, right? So if you're going to put that into this kind of simplistic picture, but I like because it shows the thing. On the right side, you have bad science, which is one result, but done only once. And the transition to good science is actually quite easy. It's the same thing, but you do multiple times and to verify it, you get the exact same ugly pink color, green color in your flask. Like that's what replicability is all about. Now, some years ago, journalists published in Nature a survey that they conducted on researchers about, generally speaking, whether they think there's something of a reproducibility crisis in their field. And this crisis may have, may have tons of different sources, right? It can be because the experiments are not documented well enough, because the code is not available, because the environment is unstable, and so on and so forth. There are a lot of sources, and we're not going to talk about all of them today, but it does give the feeling that, like, so many people think there is something of a problem. It is something serious. It is something to consider. And because it is so, sorry, 1 second. That's the general field. So like all fields, people from all fields were surveyed. And then you may think that some fields are affected more than others, which is probably the case. And you may wonder whether computer science or more generally networking research is affected by this. Well, yes, it is. Like clearly, yes. And you can find a ton of examples. I picked this one for today, which is a work that was published at NSDI last year. And I really like, they looked at how replicable are experiments that are done in the cloud, which is something that's done more and more today in networking, because just we cannot, the demand in compute is just so big that we have to run things in the cloud. And so what they did is that they looked at all the papers from the main conferences that that reported cloud experiment in the past year. And while I'm talking, you might be reading the main findings of their survey, and they are quite appalling. Sorry. Very many papers that do very few repetitions, like 3 to 10. Many do that. You have like more than half that don't even tell you like how many times they run their thing. So you just like, you report a number and then that's it. You don't even know what their wrong number is coming from. In many cases, there are no information about the spread. And yet we are talking about papers that have like massive impact on the community, like papers that get cited and work is built upon this, despite having a methodological approach, which is debatable at best, right? Not to say completely flawed. So because replicability is such an issue, you're definitely not the first one to make this realization. You might find in the literature several works or recommendation lists that have been put together to help researchers design experiments or do their research more generally. I picked 2 examples here. You might know those, you might know others. Anyway, they all have the same kind of thing in common, which is that they are mainly guidelines, right? And I read those papers and I agree with everything they say. It's great to have that, but it still lacks some concrete answers to very practical questions that I asked myself as a PhD student when I was designing my experiments. Like how many times I should repeat my experiment. How should I synthesize my results? Like, and people will tell you, you might see things that will tell you like, okay, you need to pay attention, you need to do many runs, and you need to pay attention about independence and all that stuff. But concretely, what does that mean? So bottom line, we lack a concrete methodology, which is what we are trying to provide with TriScale. And so now, here a little bit and then get into what we can do in order to foster replicability in our experiments. And so this is going to be divided in three parts, as I mentioned. So first, let's look at what variability actually is, what it looks like. So first things first, we are talking about performance evaluation. Concretely, what does that mean? What is a performance evaluation? Well, that's the basic picture. You have a certain system under tests, right? And you put some inputs to that system and you measure some outputs over there. And that's the most basic thing possible. Now, obviously, when you're trying to evaluate the overall performance of your system, you're not going to use only one input. And so you want to try out a set of inputs, and then you're going to get a set of outputs. But as soon as you get more than one value, you run into the issue of having to synthesize those values protocol might include some non-determinism, right? So we're at CPS-IoTBench. Many of you might work with wireless communication. We all know that the wireless links are not stable. They are kind of stochastic processes. So there's some non-determinism in the system already. And because there's that, we cannot just test our set of inputs only once. We need to test them multiple times. In this case, n on this picture. So n would be the number of runs we do in our experiments. But of course, the non-determinism might also come from the environment, right? Again, with wireless links, it's not just about like the properties of your radios. You have noise coming from the environment that is not under your control. And that will affect greatly, in some cases, the performance you obtain. There's also the question of measurement error, which is less of a focus for today, but is something that also in your papers. Like how do you manage to convince yourself that this is actually science, this is actually replicable? This is kind of tricky. And to address this problem, the approach I propose is that we set aside the source, the causes of the variability, which I've described some of them in the slide before, and instead rather look at how the variability look like in the data. So let's say we have the time domain in which we are going to perform our experiment here. And then you have your measurement value, y, above me, and you measure this over time, right? So in the case of banana, you want to assess energy consumption or energy efficiency. You would measure, for example, power draw over time. And that's one run. Like you and you compute the mean of your y values, well, very likely you're going to get now with the same values, right? This is going to vary a bit, at least a bit. So what do you do? Typically, when you synthesize, then you're going to synthesize again at the scale of the runs, right? And in this presentation, we're going to talk about this as KPIs, for key performance indicators. So for example, what you might do already today is that you have your values per run, and then you will compute the median of your energy consumption, right? And this is what you're going to report in your paper, and then claim 2x improvement over Q, for example. Now the issue is that you can see my time axis is still quite long, right? What happens if you make see that we're going to get a third sort of variability, right? This KPI value is going to have difference in different values, and there are some interest in the range of those KPIs. The takeaway to have for now is that regardless of the sources of variability, the performance appears to vary slightly differently along 3 different time scales. The scale of the run, which I have here, the scale of the series, and the scale over there of the repetition of series, which we call sequence. And then at each of those time scales, we have different challenges, different questions. So at the scale of the run, for example, we might wonder how long we should let the system run. At the scale of the series, we have the same question we had from the very beginning in the introduction: how many runs? How many runs should I do? But also, what's the time span I should use in order to do my series of runs? Right? Like, do you do all your runs back to back in the same hour, during the same day, during the same week? There's actually no general way to answer that question, but that's something you do need to answer and to pay attention to when you design your experiment. And finally, if you're in the mindset of doing multiple series in order to assess the long-term variability, then you face again the question of how many series should you do, right? I depict 3, but one might argue that it's not that many. So we have those 4 questions that I list here. And the goal we set ourselves was really to try to find rational answers for those questions. And that means that we want to be able to quantify the trade-off between how much effort we put in. So how many times we run experiments, how many hours, how many tests we do, and the level of confidence we get in the results. Right? It's kind of intuitive that those 2 are linked, but we would like to have a quantifiable link between those 2 things. And we've succeeded, at least I believe I do, otherwise I will not be here talking about it. And what you need to understand when I say rational answers means that I'm not going to tell you do 10 or do 100 or do 10,000, right? Rational answers mean answers that make statistical sense depending on your objective. And in order to understand those answers, we need I need to say a few things about statistics. So again, no stress. I promise it's going to be lightweight. So statistics. The first mistake that surprisingly many people do, either consciously or unconsciously, that they confuse, or they don't differentiate between a descriptive and a predictive statistic. What I mean by this, the descriptive statistic say what the data is like, whereas the predictive statistic gives some information, do some inference about what future data that has not been collected or past data that has not been collected actually might have looked like or might look like in the future. And that's what we're interested in, right? When we do a performance evaluation, thinking about the picture about replicability, we are trying to give a number that is likely to be found again if someone would do the experiment again. So it's definitely a prediction. That's what we're interested in. To put that into a picture, to be a bit more concrete, let's say we have again our banana protocol and we do our runs, right? And we measure energy consumption. We do this a number of times and that gives us a sample. Right? You can compute the mean of that sample. That's easy. You can always do that. You use the basic math you learned when you were in primary school, and then you get a description of what your sample is like, precisely what the mean of your sample is. Now, actually, what you've been doing when you've done your experiment is that those samples are actually coming from an underlying distribution of what your metric value might look like. So this is a distribution, in our case, of the energy consumption value. But you don't know that distribution. And this distribution also has a mean, right? And what you're trying to do is that based on your sample, which is what you measure, you're trying to estimate the mean value of this underlying distribution. But the underlying distribution we will never know because it is actually composed of all the infinitely many runs that one could ever run, which, I mean, you will never test, right? So as all estimation, this has some uncertainty And this is what, in the end, this is what we're interested in, and this is essentially making a prediction. Now, in statistical term, the above thing is called the empirical mean. That is the mean value of your sample, whereas what we are interested in is the distribution mean, right? Is the mean of the underlying distribution from which you assume your samples are coming from. And this is what we're after. So a bit more concretely, the descriptive statistic would be something like telling the sample mean is X, whereas the prediction would tell you that if one would draw a new sample, then the mean of that sample is likely to be close to some value X. Okay? This is a much stronger statement, and this is what is relevant for replicability. Now, in this informal example here, I'm talking about likely to be close to. Obviously, this is not really satisfactory, and we're going to see how to make that more formal. So now, to illustrate things a bit more, now we have our sample, and there is a question of which metrics we want to report, right? And something that is very commonly done is that you would pick a pair of metric, one for reporting tendency and one for reporting the variability of your data. So the central location and the spread, if you will. And so if you want to do this, many people will have as first reflex to compute the mean and standard deviation. That's perfectly fine. And you can do that to describe what your sample looked like. But does it allow you to say anything about the predicted performance, like the expected performance? If you follow what I said so far, you already understand that the answer is no. It might be slightly surprising at first because we kind of all have this picture in our head with this distribution, this normal distribution that says like about 68% of all the possible samples should lie between the mean and plus minus the standard deviation. So that seems to be able to say something about expected performance. But if you have that picture in mind, then you're making essentially two mistakes. The first one is that you're confusing the mean of the sample with the mean of the underlying distribution. So that's exactly what I talked about just before, right? It's the confusion between the descriptive and the predictive statistic. If you compute just the mean of your sample, that's only that's the mean of your sample. And then the second mistake is that this idea of plus minus, the mean plus minus one standard deviation contains 68% is only valid if you have a normal distribution. And that's a fundamental assumption that you just cannot make, right? This only works if you know that you have a Gaussian distribution or normal distribution, that's the same thing. But in practice, we work with such data, right? And in many cases, your distribution looks like something, but it's not going to be normal. And you just cannot assume this unless you know you're absolutely sure that your data is coming from a normal distribution. And I'm very sorry to inform you that I would bet that it's not the case for 95% of all the experiments you will ever do in networking. And we can discuss about why this is the case later if you want. So bottom line, those are the two kind of mistakes you're making, or might be making unintentionally, if you report mean and standard deviation with the idea that this is meaningful for prediction. And what should you do instead? Well, in order to avoid the confusion between sample mean and the mean of the distribution, you should use confidence interval. And second, you should not use statistical methods that rely on knowing the shape of the distribution, because in practice, we do not know how the distribution looks like. So I'm going to explain briefly what those two things mean. You will see it's not very difficult. So first, the confidence interval. Informally, a confidence interval is a numerical interval, so between two values. And this interval contains the true value of some parameters that we're interested in estimating with some probability. And this probability is what is called the confidence level. So to give you an example, we have again our sample here. If I say that AB is a 95% confidence interval for the median of my variable X, It means that the probability that the true median of the distribution of X, which is what I don't know, lies between A and B with a probability which is at least as large as 95%. It's a bit of a long sentence, but the concept is reasonably simple to grasp, I hope. Now, that's a confidence interval. Now, a non-parametric method is, as I said already, a method that does not make assumptions on the nature of the distribution. So if you do remember your statistical courses that you may have followed in your studies, you might have been introduced to some tests or methods, like the t-test, the ANOVA, and so on. If you don't, it's no big deal. What is important to know is that those parametric tests, they have a correspondent in a non-parametric domain. So you can do the same type of statistical analysis with methods that do or do not make assumptions on the distribution. And the difference between the two is that the parametric tests would be what we call more powerful, which means that given the same sample, they will make finer grained predictions with the data they have. Why? Well, simply because they make additional assumptions. But that's precisely the issue, right? All those tests, all the methods that I described here, and it's many more. They all assume that the samples are coming from normal distribution, which, as I said, is not the case in practice. So the bottom line is we need to rely on non-parametric methods, which are surprisingly unknown in most of the people I talk with in conferences. So 3 simple takeaways from the statistical part of the presentation. First, if we want to talk about replicability, that means that we are interested in predictive statistics, right? If we want to do predictions, we need to use confidence intervals. Like, there is no way around, because predictions are by definition uncertain. And finally, we need to use non-parametric statistics because in most cases, we have no idea what the distribution of the data actually looks like. So we need to resort on methods that do not make any such assumption. Okay, good. So before I move to the introduction of how TriScale uses all that knowledge, I'm going to make a short break here and ask for potential questions. So Marco, is there any questions so far that you would relay?
We have one question on the Slack. I think this is more a general question that is not really relevant right now, as you're talking about the statistical background. I think we can take that question in the next break.
Okay. Okay, I leave 10 seconds if there are other questions to pop up. And in the meantime, I'll take that opportunity to drink a bit. I'm trying to use a setup for the first time with those big lights that are trying to make the green screen flat and all nice, and it's extremely hot. So just be aware if you want to try something like this in your future Zoom-like life. It's getting extremely hot in here. Anyway, so no more question, no question for the moment?
No.
Okay, perfect. Then let's move on. So I've just discussed this idea that variability can be roughly classified into 3 different timescales. And I've discussed the fundamental difference between descriptive and predictive statistics and how this is important for replicability. So now let's see how we leverage all that information. So this is what I said before. We have those 3 timescales, and as you might have already guessed from the name, the framework or the methodology we've derived, TriScale, is based on this divisions in variability into timescales. So concretely, what do? Well, we look at the design pipeline and the analysis pipeline, and we divide it along those 3 timescales. Okay, and in the design pipeline, we find again the 4 questions we had I talked about in the introduction. So like, how long should my run be? How many runs should I do in a series? When should I run them? And so on. And obviously, in the analysis phase, this maps to the computation of the metrics for the run, the KPIs for the series, and the variability scores for the sequel. Okay. Now, that's the framework of TriScale. Now, let's have a look at inputs and outputs. Let's say we are still looking at banana. We set our metric. We're interested in energy consumption. So as a metric, we might pick, for example, the sum of energy consumed by all the nodes in my network. Okay, and then I'll define my KPI and variability score. I will describe it in a bit more detail how we do this in the later slide. And I feed this in my design pipeline. And this is going to go through the different questions that are there. And it's going to spit out on the other side over there a certain number of information that essentially answers to those 4 questions. And you can see the last 2 items over there are, for example, the number of runs and the number of series. And I'll explain later how those numbers are obtained. Once we know what we should do, then we can move on to the data collection part. So this is not strictly speaking part of TriScale. This is not helping you there, but you know what you should do. Now you can collect the corresponding data. For example, for energy consumption, you will collect the power draw over time. You get a series of measurements, and then you can send that in the analysis pipeline. So we compute the metrics, KPI, and variability scores. And at the end of the analysis pipeline, you will get a number of values. So the KPI per series, so you get 11 values because we've decided to do 11 series. And then you will get a variability score, which would be quantifying the amount of variation you would see in your KPI over the different series. Okay. Now, there are a number of boxes here, and I'm gonna zoom in on some of them. So one of the 2 questions we've started with, and one of the most fundamental one, if you ask me, is how many runs should I run how many times should I do my experiment? So how many runs? So let's see how TriScale addressed this. So in TriScale, we've chose to define KPIs as percentile of the distribution of metrics values. So remember, we said for banana over there, the metric is the mean energy consumption, or actually, I said just before, the sum of the energy consumption over all nodes. So replace mean by the sum over there. But anyway, it doesn't really matter what the metric actually is. We define KPI, as I said, as percentile. And the good news is that we can compute confidence interval for those percentile in a non-parametric way. So that fits the bill in terms of statistical methods, right? It is non-parametric. That means that it doesn't matter what is the shape of the underlying distribution. And it gives us a confidence interval, which is what we need in order to make our estimations. And I will give you first a visual illustration about how we can do this, how we can construct those confidence intervals. So let's start with this very basic example. Let's say we're measuring a quantity X, so our metric, which would be the energy consumption. I said the sum of energy consumption of all the nodes. And if you do it only once, right, you take one sample, what is the probability that this one sample here is above or below the median of the underlying distribution? Think about that for a few seconds. The probability is going to be 50-50. Why? Well, because it's the definition of the median, right? The median of the distribution by design, by definition, is the value that divides the entire set of possible values equally on each side, right? So if you take one value in this entire set, then you have 1/2 probability that you pick a value that is in the lower half, and 50% chance that you pick a value which is in the upper half. This is all fine. And now it gets slightly more interesting when we take a second sample. And if you make the assumption that these samples are independent from one another, then the probability is going to multiply with each other. And so the probability that the true median is lower than the two, like this, that the 2 samples is 1/4. Above the 2 samples over there is 1/4, and in between 1/2. And guess what? You can do the same thing with 3 samples and with 4 samples and so on. And if you look a bit at the values in the graph, you might already recognize that actually it generalizes by saying that the probability that any percentile lies between two successive samples follows a distribution which is well known, which is the binomial distribution, where here n is the overall number of samples we have. And this is very nice, because if you work on this a bit, which is very simple math, you can come up with an expression which is like this, which gives you the probability that the sample xm is smaller than a certain percentile. And if you think about it, this is a confidence interval. This is what gives you a bound, which is xm, on any percentile, and you have over there on the right side of the equal sign, the probability, right? So the confidence level. And so we can just use this to build confidence interval for any percentile we like at any confidence level we are interested in. And it gets even better. If you work slightly more on that equation, you can actually flip it around to extract n. And then it gets very interesting, because remember, n is the number of runs we want to perform, or we have performed. And what this equation gives you is actually the minimal number of runs n that are required to estimate any percentile p at any confidence level c. So with numbers, here's what it looks like. Let's say we fix the confidence level at 95% over there, and then we change the percentile. So if you look at the median, you plug the numbers in, and it will return that you need a minimum of 6 samples in order to estimate your median, or to build a confidence interval for your median at 95%. Okay? And then if we increase the percentile, or decrease, but that's symmetric, then of course the number of runs changes and tend to increase, right? With a quartile, say, okay, we need 11 runs. But then if we look at the first percentile, it already blows up to about 300 runs. And then if we look at the 0.01 percentile, which correspond to this idea of 5 nines replicability, or 5 nines performance, whatever the performance might be, then the numbers blow up to 300,000. Right? So between you and me, I don't know anyone that runs the same experiment 300,000 times. So strictly speaking, what this is telling us is like how much effort we need to put in at minimum in order to make performance claim at 5-9 reliability, for example, or 5-9 confidence. Okay, so in a more dynamic view, here is how building the confidence interval looks like. So we're still doing the same, 95 CI on the median. If I have one sample, I cannot see anything. 2, 3, 4, 5. And eventually, when we get the 6th sample, then we know, or the math tells us, that the entire range of my values is my CI, my confidence interval. And then if I keep increasing my number of samples, 7, 8, when I get to 9, then the math will tell you that you get a 95% confidence 95% confidence interval for the median by excluding the most extreme values on each side, which makes sense, right? The more data we have, the more precise we can make the estimate. And if we keep going and we keep increasing the samples, what you see is that in general, the more samples you have, the narrower your confidence interval is getting, right? And how narrow you want to get, well, that's for you to say, but if you want to get it very narrow, then you need to put in more effort. Okay, so that's about defining how we pick the number of samples we want to use. Now, how about the second question we have at the beginning, which is how to assess replicability? So again, reminder, replicability, we're talking different data, same analysis. And as we've discussed, this is kind of about qualifying that the results are the same. And here we have a bit of an issue because most statistical methods are very good at checking that things are different. They are good at saying that 2 samples, A and B, come from different distributions. So for example, you would do like a test for medicine, and then you would have a control group that got placebo, and then you get the group that is under the medicine, and you want to see that the medicine people get better. For the COVID vaccine, for example, that you want to see that the guy that got the true vaccine actually get less infected. So you want to see that things are different. But we have the reverse problem here. We want to see that the things are different. Not that the thing is different, but that the thing is the same. And the problem is that similarity tests, or what exists that could be qualified this way, boils down to testing that the differences are smaller than some threshold. So we're starting to think about a way that could be used in order to set those thresholds, but generalize well, because like all experiments and all fields are kind of different. And we failed finding a good approach for doing that. I'm not saying it's impossible, but we didn't manage to find anything satisfactory. So instead, what we chose to do in TriScale is that we do not assess replicability as a binary criterion. It's like you're replicable or you're not. But instead, we chose to quantify it. We quantify the variability. And as you might already understood, this is what the variability score is going to help us do. And so the variability score is the artifact or the statistic we use in order to quantify the variability of an entire experimental pipeline. And we use the exact same approach, and that's kind of like one of the beauty of it, as for the KPI. So here, kind of same figure, we define the variability score as a range between percentile values, but now not computed on the metric, but computed on the KPI. So this is what you see on the right over there, right? We have the KPIs for our 3 series, and then we're going to try to estimate the range of values for the KPIs over time. Right? And this is what's going to capture the long-term variability we are after for replicability purposes. So the point is that we compute the variability score, but we do not, or TriScale does not say this is replicable or this is not. If you shall need this binary cut, then the suggestion is that you should base it on the variability score. And that's going to be context specific, right? If you're doing localization over ultra-wideband, or if you're doing data collection protocols, you're not going to use the same threshold, right? It doesn't really make much sense. The threshold needs to be context specific. But in both contexts, you can use the variability score and all the processes that are behind there to get to the score. And you know what the score means. You know what the statistical meaning of the score is. So we're back to the pictures, the overall picture of the TriScale framework. As you see, I've talked about how many runs, how to compute the variability scores, which of course relate to the computation of KPI and how many series. There are a few other boxes that I do not have time to cover in this tutorial. A number of things that are important to be aware of. First, there is the question of independence. Right? I mentioned this in passing when we were talking about the Thompson method to compute confidence interval. Independence is fundamental. We pretty much cannot do anything without it. So the issue is that in many cases, we do not have the power to guarantee that the design of our experiment guarantee independence of the data or between the different samples. But what you can do and what you should do and what TriScale does is that we empirically check whether the data we collect appears to come from an independent experiment. And if you want, I can go a bit more into details about that in the questions. There's the issue of the convergence of runs, right? So when we're looking up there at the number of runs, it's necessarily going to be finite, right? You cannot run your variable forever. The census deadline is X day. You cannot run forever. It needs to be finished at some point. So how do you do to guarantee that your run is actually converged, right? Like if you have a power profile which is like this, well, you see that there is some uptrend, and it's not good, right? So how do you assess this? In networking, very often we have this issue of seasonality, which means that we have patterns in the data. So typically, if you run wireless experiment, you have more interference during the day than during the night. So performance is almost always better if you run at night than if you run during the day, right? So that's something that is important to take into account for replicability, because if I run my experiment every day and equally spread across the day, including nighttime and daytime, And then you come with your crazy banana thing and you run only at night and you say, hey, I outperform you. It's cheating, right? Like you're only testing in the right case. And if you do that on purpose or not, then you're breaking the seasonality or you're neglecting the seasonality in the environment. And finally, there's the question of how to compare confidence intervals. There's something I did not really talk about, but once you have, when you have single values, it's quite easy to compare. Once you have intervals, it gets slightly more tricky. It seems simple at first, but when you dig into it, you realize it's actually not so simple. So TriScale helps you addressing the first 3 points. The fourth point is not strictly speaking part of TriScale. It's kind of like an orthogonal thing. We have been working on this, and hopefully we'll be able to present that in a future version of the tutorial. So there are a lot more, as I said, a lot more boxes I didn't talk about. There are a lot more in the paper. You can find it at tiny.cc/TriScale. We're also on the TriScale website, which we're going to go to in a minute. So you're going to see what it looks like. And so now in a second, I'll take the second break for questions, which will be followed by the hands-on session. Before we do this, a quick summary on what we talked about. So I started this presentation by motivating why replicability matters. I hope I have convinced you that it's something worthwhile putting some effort in and documenting ourselves about how to foster replicability. I've showed you how this can be done, and hopefully I've managed to convince you that it's not honestly so difficult. And we have strived to make the tool, which is TriScale, as handy as possible, to make it as easy as possible for you to apply the method, even though you don't necessarily understand all the subtlety of the statistics underneath. And we're going to do the hands-on session in a second. Okay, so now we have plenty of time for questions. So how are we standing, Marco?
Yeah, I think we should now take Neil's question that you posted on the Slack. So the question is, if you're running your experiments on a time-shared resource like FlockLab, how do you balance the need for repetition with the needs of other users to use the platform for their experiments? For you, more experiments is better. But if the resource is fully subscribed, then repetition of your experiment requires someone else doing fewer experiments.
Yes. I have a very clear and very sad answer to you, is that you're screwed. if the resource is fully booked, there is not much you can do. Now, it doesn't mean that every hope is lost. What is important is that you understand what you're able to do. Like if you cannot run more experiment, you cannot run more experiment. And there's no point of saying like, you should run 1,000, right? But if you're only able to run 10 or only able to run 15, or 3. That's what you can do, right? But what you can and what you should do is to make performance claims or claims in your paper that are compatible with the amount of experiment you've been able to run. Which means that if you've been able to run only, I don't know, let's say 10 runs on FlockLab, then you will not be able to say anything about or anything meaningful about the tail performance of your protocol. Like the performance at the first percentile, because you just didn't do enough runs. But you already have enough to be able to say about the median performance, like we had in our banana example throughout the presentation. So it's all about, you can revert the thing, right? Like you can use TriScale to say, if I define my KPI like this and that, how many runs I need. But you can also say like, this is what I have X runs. Can I compute a confidence interval for this KPI, for the median at 95%, or for the 75th percentile at 95%? And you can see whether that fits or not, and TriScale will tell you what is the confidence interval then, with the number of runs you have available.
Thank you.
There are no further questions on Slack or Zoom, but
I have one actually.
Yeah, please go ahead.
Yeah, so kind of following on from the last question there, actually, about what happens if the resource you have is fully booked. If you were to use these techniques to develop some sort of simulation, are you then able to kind of quantify the validity of that simulation using these techniques, and then use that simulation in order to generate new results? And then are those results still valid?
Yes, so those results do not necessarily, I mean, all I talked about is definitely valid in simulation as well, and in the way you define your experiments and so on. Simulation is quite interesting for several reasons, is that, well, because you simulate everything, you're under control. So you can define how much variability you put in your environment, you can define how much randomness you put in, and then you can design your experiment, or you can size your experiment based on this information. You essentially kill off the problem we have on Flock Lab between day and night, for example. If you run a simulation, and if we forget about the issues with the load of the machine on which you run your simulation, then you can guarantee independence, which you cannot do in general in the real world. And you can, well, if you have the time or the budget, you can run as many runs as you want, right? So I'm not sure to which extent that answers your question, but we can definitely use those techniques in simulations as well. And you can also like use them in order to get an idea of what you expect to find in a simulated environment. And then you translate to the real world and see how much difference you have, which is of interest for some people. But I mean, I know of a use case of that, where you run both things in simulation and real world.
Yeah, exactly. I was specifically thinking of we're doing a lot of drone work out here, and a lot of the drone stuff is use this as this gazebo sort of simulation. So I was thinking more along those lines. But yeah, thank you very much.
Other questions? Yeah. Okay, if there are no questions yet at this point, then I propose that we start with the hands-on part. So here's how it goes. So I invite you now to open a browser window or whatever you like, but I strongly suggest you use your laptop and then your smartphone. And you go to triscale.ethstat.ch, and you're going to see a page that looks not anymore exactly like this, but you should fall on this page. It might be that if you enforce HTTPS, you have to overrun this because sadly, GitHub does not provide what I need for that to work. But anyway, you can trust this website. This is actually just a rendering of the GitHub repo. And you're going to fall on this page. And if you don't have to bother reading all that stuff, there is a first section which is called tutorial, and this launch binder button here. And you can just click on that. And if you click on this in a second, you will see some thing appearing, hopefully. See, this is what happens when you have to switch to Wi-Fi. Everything gets slow. So it's going to open a binder. And short story, binder is a very interesting and amazing tool, which is provided for free, which allows you to essentially turn a GitHub repo into an actionable and runnable file in your browser. So here you need to select the kernel, just let the thing here. And then you enter a Jupyter notebook. So for those of you that are not familiar with Jupyter Notebook, don't worry too much. There's actually not much to know. What you need to know is that the notebook is composed on a sequence of cells. Some of them are code, some of them are text, and you can execute the code. So the most handy shortcut to execute the code is to press Control and Enter, which I'm just doing now. And you can see here that while it executes, there is a small asterisk, and then you get a number, means that this code cell has been executed. This is Python. So you don't necessarily need to know Python in order to follow the hands-on part. If you have any questions or issues, I will be able to help you. So we're going to do together this, what I call part 0, where we're going to keep working on this performance evaluation of our banana protocol. So how do we got to those numbers that I showed in the presentation? Well, it's quite simple, right? the first thing you have to do is to define your metric, but this is kind of independent of TriScale. You can pick, as I said, you can pick pretty much any metric you like. And then you need to define your KPI. And the KPI, as we said, is the combination of the percentile that you're trying to estimate and the confidence interval for that percentile. So we say we're interested in the median performance with 95% confidence. So we execute that. And then we can only, the only thing we have to do is to call one of TriScale API function, which is called experiment sizing, that takes the percentile in confidence and is going to return to you the minimal number of samples you need in order to make that estimation. So that confidence interval at that percentile. And that's it, right? So it tells us that we need a minimum of 5 runs. And because we use the same method, we can do the same thing for the variability score. So here in the presentation, I use the range between the 25th and the 75th percentile with still 95% confidence. And here it returns that we need a minimum of 11 samples. So because we're talking of KPI, that means we need 11 series of 5 runs. That is overall 55 runs of our experiment at minimum in order to be able to compute that variability score. All right. And then, okay, so we need a minimum of 11 series. There's more explanation about what it means, right? And here is the last important things that I want to talk about how to interpret those values, right? I talked a lot about like, don't do this, do that. But practically, what does that mean? By definition of how we define, whoops, sorry about that. By definition of how we define the KPI, it means that in one series of runs, so in one series of 5 runs in our case, the median value for one metric for one run is going to be lower or equal to the KPI value with a confidence of 95%. Right? So you take a set of runs, 5, 10, 20, 15, you get those metric values. The values you get are what you get. Based on this, you compute a KPI based on what TriScale is giving you. You get a numerical value, and you can interpret it as follows, which means that if someone else is running the same series with the same or different number of runs, they are likely to get a median value for their series that's going to be based on that KPI. And the similar statement hold for the variability score. So I let you read this, and then the rest of the notebook is structured as follows. There's the first part about experiment design that goes a bit into more details about the math behind this equation here, which is fundamental to tell us the minimal number of runs or the minimum number of series. So there are some explanations about essentially how the TriScale API looks like. And then at the end, you have a number of small, quite easy questions that I would ask you to invite you to try to answer. So what are the minimal number of runs required to estimate the 95th percentile with 90% confidence, for example? So that is meant to be fairly easy. It's just to get a feel about how the API looks like and how to use it. And then there is a second part on data analysis where provided in the repository, you already have access to some data that is coming from experiments, from real experiments that I've actually done. And with the presentation of the API for the analysis pipeline. So how to analyze this data. And then you're invited to see, to play a bit with the definition of the KPI and the variability score and see how the numerical scores vary. That may take a bit longer time, and it's kind of flexible. If you want to spend more time on this, you're welcome to do so. Okay, so then equals and variability score, and then in the end you have again a small set of questions, some helpers function that I wrote for you. And eventually, some short questions for you to try to answer. By default, all the cell runs, right? So you can just like press enter, but if you don't read the text, you're gonna kind of miss the point. And yeah, so the plan now is that if I'm not mistaken, we have about 15 minutes left on the timing. So I would invite you to go and have a look, try out the API for yourself. And I'm of course here to try to answer any questions. Please do it by voice. That will be easier for me to catch. Otherwise, I'll start monitoring the chats as well. I hope you've enjoyed the tutorial. I hope you've learned some interesting things, and hopefully that might influence the way you're going to design your experiments in the future for the better. At least I hope. Thank you very much, everyone.